I've said in several videos now that the big idea here is that parametric equations separate the relationship between x and y. So you don't have a single equation where y is directly related to x with an equation. Instead, x is related to time and y is related to time in a different way. So we've been going through all of this work to figure out how can you graph the path for a set of parametric equations. We've been making tables and we've been using those tables to plot points. Can't you just go directly from here to there? Can't you just take these two equations and combine them together so that there's no t anymore and you're just understanding how's the y coordinate directly related to the x coordinate? And the answer is sometimes. You can think about this as solving a system of equations if you want. The idea is let's isolate t and then plug that value in for t in the other side. And that's going to eliminate t and give us an equation that has no time. So what would that look like? Let's take our x equation here, x equals t plus 2, and let's solve for t. So t equals x minus 2. All right, so now that I know that t equals x minus 2, I can take y equals root t, and I can plug that in for t. So that gives me y equals the square root of x minus 2. And now I've got a graph that directly relates x coordinates and y coordinates. You guys know that this is a square root function that has been shifted right by 2, so you would expect it to look something like that. So that process is called eliminating the parameter, and we'll do a couple of them. But really what makes parametrically defined equations so special is they'll let you describe paths that would be very, very difficult to describe in a rectangular way. So for most of the interesting parametric equations we're going to be working with, if you try and do this process, you're going to end up in an algebraic mess because you're trying to describe, a graph that looks like this. This is the path that a rider would take on the teacup ride at Disneyland, potentially. And even though it's a very, very complicated looking graph, the parametric equations that define it are actually very straightforward. So that's kind of why they're so powerful. It's because you can use simple equations to describe interesting and complicated paths. And we'll get there. Probably not today, probably not tomorrow, but maybe next unit. The other thing that you lose when you convert from parametric equations back to a rectangular equation is you lose all the timing information. So I'd said that this describes motion along a path. This tells me what the path is, but it doesn't tell me anything about how a point would move along the path, where it would be at different times, anything like that, because we've thrown away all the time information when we solved for t and eliminated it. So, in summary, it's sometimes a helpful thing to be able to do, but usually not. Let's just do a quick self-check. If x is root t plus 4 and y is root t minus 4, go through the same algebraic process of solving for t and substituting to eliminate the parameter. If you're wondering whether you can use elimination as a technique rather than substitution, you could absolutely do that as well. And I'll show you what both of them look like in a second. But first, use whichever technique you want and figure out what's the equation. All right, so if I'm going to use substitution, I guess maybe I'll isolate the t variable in the x equation. So I've got x minus 4 equals root t, because I just subtracted 4 from both sides. Now I'll square both sides, and that gives me t equals quantity x minus 4 squared. So now I can plug that into the y equation. So instead of root t, I'll write root x minus 4 squared, and then I've still got the negative 4 on the outside. So we know that squaring and square rooting are opposites, or can't believe I just said opposites, are inverse functions. So they undo each other. So now I've got x minus 4 minus another 4. So this is just the line y equals x minus 8. There's one technical detail to pay attention to here. This set of parametric equations is only defined for times greater than or equal to 0, because otherwise you'd have the square root of a negative value, and we're not working with complex values right now. So what does that mean for the domain restriction on the resulting equation here? Well, one easy way to think about it is think about what's the x-coordinate when time equals 0. So when time equals 0, the x-coordinate is 4. and the x-coordinates are only going to get larger from there. So that means that we now have a domain restriction that x must be greater than or equal to 4, because it's not possible to get other x values with the original time restriction. Let's do it again by elimination. So if I've got x is root t plus 4, I could subtract y equals root t minus 4. So let's subtract. So here on the left-hand side, I've got x minus y. Here on the right-hand side, I've got root t minus, that's supposed to be a t. I've got root t minus root t. So those cancel each other. And now I've got 4 minus minus 4, which gives me 8. So now if I just reorganize, I'll move the y over here by adding y. I'll subtract 8 from both sides. And I've got y equals x minus 8, which is the same thing that I had over there. And then the discussion about the time restriction causing a domain restriction over here still applies. So, you can use your techniques for solving systems of equations that you learned last year as a way of eliminating the variable, either by substitution or by elimination.